Okay, so it took us a while, but it works now. So once again, give a warm hand to Pablo, and we can start. Sorry for that.
Hello, hello. Okay, so first of all, thanks to Chris and everyone who helped me set up the stuff for the presentation. I see some familiar faces here. Some of you might know me, might have seen me in these corridors. So yeah, my name is Pablo Ribalta. Today we'll be talking about AI in healthcare at NVIDIA. Maybe a little bit about me. I lead a team in NVIDIA in Warsaw of applied research in AI in healthcare. So basically what we do is that we use deep learning. We try to attack different medical problems. Have you guys heard about deep learning? Any of you? Raise your hand. Okay, do you know what it is? Could you explain it to your grandmother? Well, there is this thing that you don't understand something unless you can explain it to your grandmother, so I'm not sure if I would be able, but I do my best. Anyway, so let me start by changing the slide. I got too far, maybe. Well, I will have to stay close. Okay, so let's start from the basics. You hear nowadays artificial intelligence, you hear machine learning, deep neural networks. These are like a storm of words and buzzwords, and you don't know what you are hearing anymore. I want to start by setting up the stage a little bit. In this circle, you see that artificial intelligence is this dream that we have as computer scientists. We want machines to be intelligent. We want them to make rational decisions. That's scary. We don't want them shooting rockets at our enemies. That's not what we want. But we want them to help us to make intelligent decisions when we drive, when, for example, taking care of our health. But we are still very, very far away from it. Technology is still very primitive. But this moonshot. I don't know, some years ago we had never been to the moon, but some people decided that we wanted to go there, and that's what's happening right now. We are at the very beginning of this. Inside what is artificial intelligence, we've seen some classifiers, some things like that. So there is machine learning. This is a subset of artificial intelligence. Machine learning is about, instead of programming a machine to do something in particular, we want to teach this machine to do it. I'm sure here you have all, practically everyone, written some code. You know that writing code is a pain in the neck. You forget something, you have to write perfect syntax, you have to write perfect logic, and that is complicated. That's very difficult. If you want to make a program, for example, to tell you your age, that's very easy, but if you want to teach a machine to play chess at a professional level, or to play Go, or to play StarCraft, that's very complicated. Instead, what we can do is try to teach a machine to let a machine learn to do it by itself. So this is basically machine learning. For this you have many different methods. One of them is deep learning. Deep learning is yet a subset of machine learning. It's a little bit different. Why? Because it's deeper. No, it's not because of that. Deep learning is a little bit different than regular machine learning in a sense that we've seen before that a lot of work goes in picking features. You want to let the machine learn to do something. So you have to tell the machine what is useful, what's not. So like this it will focus on what matters and improve its decision making. However, sometimes not that easy. Sometimes what you want is to say if this photo is a cat or not. It's like a very important thing you want to figure out. So what makes a cat a cat? You can say, well, if it has 2 ears, if it has 2 eyes, if it has mustache, but this could be Salvador Dali, for example, instead of your cat. So how can you really really make sure that you pick the best features. Does anyone want to answer this question? Okay, I will do it for you. So you let the machine figure out what are the features that are important. You make feature selection part of the training. You have a classifier, and the step before the classifier is where the machine learns to differentiate, learns to discriminate, and then you find out that it can figure out if this is a cat or not, maybe because of the color, or maybe because of whatever. It doesn't have to do with the mustache or not. So yeah, in this slide, I go a little bit into more detail on that. Deep learning is modern reincarnation of artificial neural networks. This all sounds very hot. We all see Google, we all see NVIDIA, we all see Microsoft, all the companies doing crazy stuff, but this stuff has been around since the 70s. It's not like rocket science that we are doing nowadays. This is old stuff. What has changed? Any idea?
We have GPUs.
Yeah, that's it. Nowadays we have GPUs, which are supercomputers in your own computer. It used to be that, I don't know, a GPU would allow you to play Crysis 2. Nowadays, GPUs allow you to do anything. You can mine Bitcoin. You can, I don't know, do high-performance computing. You can do deep learning. Because they power just simply an insane amount of computing power. So what's new in deep learning is this layered network architecture, as I mentioned. Now you don't have only a neural network classifier. You have some layers in the beginning, which do the feature extraction. Now we can do that because we have GPU. We have new training math. This is one of the latest developments. You know that when we work in binary, we have different types of encoding. So if you want to represent floating numbers, so typically you use 32 bits. Nowadays, you can do floating point operations with 16 or 8 bits. So I don't know, like this might be advanced math, but follow me. If you have 32-bit float and you can do one operation, if you have a 16-bit float, how many operations you can do? 2, because where you do 32 bits, now you have 2 times 16. If you have 8 bits, so you can do 4. This is a massive game changer because we have fast GPUs, but now we are even faster because of the math. And then we have scale. We have super large data sets of, I don't know, millions and millions of images. We have super large clusters that we can use with tens or hundreds of GPUs. So this is a total game changer because this allows us to tackle problems beyond, is this a cat or not, which seems relatively easy, but that's complicated. But we can teach machines to play Go, to play StarCraft, etc., which is like super complicated, or to drive cars. The benefit of deep learning is that it's much more accurate than traditional machine learning because it picks the features that he wants and it combines them in a way that it makes sense. It learns these features from raw data, so you don't have to kill yourself, trying to, do crazy things with it. And there's no feature engineering required. I had this written before your talk. It's not like any answer to anything, but you don't need to do any feature engineering. So at the end of the day, what happens with deep learning is that it totally rebalances the effort that you require to innovate on stuff. You don't have to download the data set, read it, go through it. You have to do that. You need to understand your data. It's very important. But the time that you have to spend, tweaking everything changes. In traditional computer vision, for example, the largest part of the work is feature engineering. What does it mean? We download the data set, ImageNet. 12 million images, the Olympic Games of computer vision. Imagine going through 12 million images of 1,000 different classes and figure out if this is a sheep, this is a frog. This is insane. No one will do that. And be alive afterwards. Then you have data preparation, which takes big chunk of your time. Then you have numerical optimization, so basically you sit down, let everything run. And then you have model architecture. In traditional computer vision, what you have is several models that are more or less figured out. You tune the hyperparameters, you make them run, sort of try to pick the best based on your model, on your data, sorry. But in deep learning, for example, when we use convolutional neural networks, the whole thing just changes. We don't need to do that much feature engineering because we download these 12 million images. We have them labeled, but we don't have to go into, how many edges do we have in this picture, how many, I don't know. You just skip that part. What you do is you figure out the data distribution of your data, you normalize it for better processing, you do other kinds of things. Numerical optimization still takes a big chunk of your time. Sorry, data preparation takes also some time, because basically what you want is to load this data the most efficient way. And numerical optimization takes a lot of time. Numerical optimization is, okay, sit down, relax, you are going to be here for a few hours. Basically the way it works is that the more data that you have, the more you can learn. It's like the brain, the more you teach it, the more it learns. But the fact that it takes so long is because the problems that we can attack nowadays are also much more complicated. We see that in red we have one large portion, is the model architecture. This is where everything just changes. Here we can spend really a big amount of time, sit down, work on our model, try to squeeze the last bit of performance. We are not using cookie cutter recipes. We can build our network, we can change hyperparameters, we can really play with it. And we can really advance, because there is much to be learned. There is a lot of people doing deep learning, but believe me, the possibilities are just endless. A lot of new insights are discovered every day. So, these pie charts are not real data. This is based on my experience. Your experience might be different, but I asked around and more or less everyone has the same experience. But this brings us to the question of how much data is just enough to train deep learning. Well, the more the better. But there is a point where the more data you add, the more you learn is not linear. It starts falling. You will learn more, but not so efficiently. The general rule of thumb is that you need more than 5,000 positives per class in order to be able to learn to extract features. And the key is to have good, relevant data. We saw in the previous presentation that you can take a mountain of garbage data, you can steer it around until it gives the results that you want, you make your boss happy, everyone is happy. But when you try it in the real world, this thing is going to fail. If you put garbage in, you get garbage out, and that's not what you want. You need good data. So, okay, that's cool. If I want to run it at home and show off my cousins, how well this thing works, show it to my parents, but where can machine learning make the biggest impact? One area that machine learning can be a game changer is healthcare. Here in this graph, in this chart, you can see, for example, the amount of, the proportion of radiologists per inhabitant that you have in different countries in the world. You see that in the United States, they are very close from the ideal threshold. So they have like 2,500 people per radiologist. It means that one American radiologist is responsible for 12,000 people. Fine. But other countries don't have it so great. The scale is logarithmic. So you can see that, for example, in Tanzania, one radiologist has to take care of more than 1 million persons. That's not cool. Countries like India, Thailand, Indonesia, Ethiopia, so they also have some problems in that regard. So this means that, for example, in healthcare, there is a lot of data to go through. Just a lot of it. When you go to the doctor because you broke a bone, or because they need to do you an MRI, or because you need to do a CT because, I don't know, whatever. This takes the doctor roughly around 40 minutes. Imagine if you are a radiologist, very well trained, and you've been, for example, working for 8-10 hours, you are not that effective anymore. Why? Because you need to go through a collection of slices of images of a person, and you can have like 100 images and only one shows the lesion that you are looking for. This is not, this is very tiring. Expertise also is limited. As you see here, for example, there are not so many radiologists, so if you are in a forest or jungle in Tanzania, it's highly unlikely you will have a radiologist nearby. So here we have the opportunity to provide something that can help practitioners, can make their life easier. You go from, for example, 40 minutes analysis to just a few seconds. Plus, you can have this thing everywhere. You can just have a computer, connect it, and you can have it wherever. It doesn't matter. That's pretty cool. So I will talk to you about some of the challenges that we work on at NVIDIA Healthcare, some of the problems that can be attacked through deep learning. You will see some examples. The first of them is, for example, diagnosing diabetic retinopathy. So the way it works is that diabetic people, because of their condition, have a propension to develop problems with their eyes. This is complicated to analyze. Requires an ophthalmologist to sit down and really look at your eyes. So one of the things you can do with deep learning is to teach a system how does a healthy, this is called fundus, no? Analysis of retinal fundus images. So it's like the bottom of your retina. So what you see here in orange is like the interior of your eye and all the blood vessels that go from it. So on the left you have an image of a healthy retina. Basically, that's how you want your retina to look like, healthy. On the right, you have a diseased example. You can see some marks, some hemorrhages, where basically, because of their condition, some changes, some lesions appear, and their vision is affected. This, for example, can be done if you train a network to differentiate between healthy and diseased. And moreover, not only this, you can classify to which grade of diabetic retinopathy you have. You can say that you don't have. You can say, well, it's mild, moderate, severe, or proliferative. You want to go as close as possible from blue. How do we do this? Well, take a data set. We are talking about a data set of 800,000 images. We hire 54 ophthalmologists, and we have them label them. We use their expert knowledge to label these images. And what we have now is a model that can be deployed anywhere, and that agglomerates the wisdom of these 54 ophthalmologists, and that can be deployed, for example, in your mobile phone. Then it doesn't matter where you are, you have an instant way to check it. Here we are talking about a convolutional network of 26 layers. Unfortunately, it's very small. I didn't know how to make it fit. But this is a pretty big network. What we can get out of it is, for example, a classification, tell us what is the grade. But different things. It is a high quality image, left, right eye, etc. Another problem that we can tackle in deep learning is dementia or Alzheimer. As you see, a lot of people in the world have Alzheimer, doesn't matter your continent. Curious is that the more you advance, more people have it. It's because healthcare gets better, so people live to a longer age, where they can develop this kind of, condition. This condition is, I'm sure you know, it's very bad. And the question is that we want to address it as soon as possible. We don't want to wait. We don't want to live in a world where people can arrive to this stage and it's too late to do something with them. Using machine learning, we don't know, doctors don't know why this happens. The problem with this disease is that we don't know it happens. Or we don't know what are the causes that lead to it. But using machine learning, we can learn from patients who were healthy 10 years ago, and today they have developed this condition, and we can let the neural networks figure out what are the features that mattered and that led to this situation nowadays. It's pretty big. And this nowadays is being done. How many of you know TensorFlow or PyTorch? Have you ever heard something like that? Okay, very good, very good. NVIDIA has its own framework called NVIDIA Digits, which is very similar to TensorFlow and PyTorch. I invite you to try it. It has more than them. It has the whole training pipeline. But people in our group has used it to diagnose or to find markers of Alzheimer's disease before it happens. And that's pretty great because none of the members in this team has medical studies. How great is that? You have no idea about medicine. You know how to make machines learn. And thanks to this, you can find insights that can help doctors, revise their treatments. That is just huge. This team developed an end-to-end diagnostic platform that has all the different parts: data acquisition and conversion, data preprocessing and preparation, classification, etc. Plus, and it's ultra fast. It just works in, boom, 1 second you have it. This increases the throughput, of course, from every doctor. But as I said, the most valuable thing are the insights that we can produce. We can create science with this. And you might say, well, I just want to run some models in my house, play with it, I don't know. But maybe there is this problem you are passionate about. I don't know, for me it happened to be healthcare, but for you it might be something else. For you it might be, for example, football extra-class betting, and you might get rich. Yeah. But you might think that it is stupid, but you might end up finding this key insight that can help. That's what I find the most inspiring thing about my job. Another of the problems we work on is cancer detection. Sometimes you are not feeling very well, you go to the doctor, you have some problems, and they have to run you this whole body scan, and then the time is critical. Because if your illness is very advanced, then it's a problem. In particular, in this case, I am focusing on brain cancer. This is one of our use cases. And well, brain cancer is very complicated. The brain is a very sophisticated organ that we understand very little from it. And well, as you see in the slide, there are a lot of different brain cancer. It's not like you got brain cancer, boom, this is the standard definition. No, there are more than 120 different types of brain cancer. That is just a lot of them, a lot of them. I don't know, what do we have here? There are only 4 treatments for brain cancer approved by the FDA. It's not a lot. But the bottom line is that brain cancer, you want to catch it as early as possible. It is a pretty serious thing. In the last year, there is this challenge called BRATS, which is part of a conference called MICAI, which is machine learning applied to healthcare. That happens every year, but this BRATS is like, as I said before with ImageNet, is like the Olympic Games of medical image segmentation. The goal of this challenge, which happens every year, is to given different patients and their brain MRI scans with different modalities, what you want is to find their lesion in the most accurate way. This happens every year, and last year, one of our guys won BRATS with the top result historically, so it has been running for like 10 years, so he just beat everyone. And he was able to do it because he aggregated the images from all the modalities in order to perform the final decision. This is difficult. First, because it really needs you to know what you are doing, of course. You need to have the expertise. But you also need to have the technical platform to be able to run this. Why? Because without the GPU, this is impossible. This is an incredible amount of data. The model is not that complicated. Probably I will not go into detail. I don't want to bore you to detail. But what you need to know is that when they take you a scan, they have a different modality images that show different things about your brain. And he was able to put everything all together in a model that would learn from every modality and produce an answer. That was great. I have a small video. I don't know if it will work. Which shows a little bit. It's just 1 minute. So what we see here is a 3D volume as you want to segment it. These are not 2D images, these are 3D volumes. In blue, you see the lesion itself. In red, what you can see is the hematoma, so like the, fluid going out of the lesion. This platform for visualizing is provided by a company called Infusion, with whom we work directly. This software is used by doctors around the world. So, yeah, everything that the network sees was this volume that we saw before, and the network is able to put things together and provide you the answer. So yeah, to see more of the cool stuff we do, please go to NVIDIA Research. You will see a bunch of stuff. Okay, so you might say, okay, all these things are very cool, but I don't work at NVIDIA. That really sucks because I cannot do anything like that. Well, you are wrong because you can do it. There are two things that NVIDIA provides you. You probably don't know about it, but now you know about it. NVIDIA provides you with containers. It's called. How many of you have heard about Docker? Okay, very good. So Docker is a technology that is like a virtual machine on top of your operating system, and you can deploy on top, so different software which will run emulated. And then it's NVIDIA hardware that you can go to MediaMarkt and buy some. Okay, so let me talk about containers. What are NVIDIA containers? So NVIDIA containers are, well, when you want to go into deep learning, that's just, I remember in the beginning, it was just bad. Why? Because you had to install CUDA, you had to install cuDNN, you had to install TensorFlow, and the version of TensorFlow is not compatible with cuDNN, so you have to uninstall cuDNN. You install the newer cuDNN, and it doesn't work because you need to install CUDA first. So you need to uninstall cuDNN, CUDA, then install CUDA again, install cuDNN, then TensorFlow, and pray that you didn't install TensorFlow for CPU, because if you did, you have to uninstall it and install GPU version. So that's not very cool. Then you want to change to PyTorch, and you want to use PyTorch, and PyTorch doesn't work with your version of CUDA. So what you do, I don't know, but you don't want to continue. You say deep learning, that's not cool. So that it's cool. So NVIDIA realized about that. So now it provides everyone with containers. Containers, well, we have a flavor of Docker, which is called NVIDIA Docker. That is the same as Docker, but it has integrated driver support for your GPU. The problem with Docker is that you install it on your machine, but it doesn't have any way to connect to the native drivers of NVIDIA. So you cannot use CUDA. So you say, well, that sucks. Well, so NVIDIA figured out that for you. And now you can install NVIDIA Docker and just simply pull a container that will have from the registry, which will have any particular version of CUDA, and will come with any major framework that you want to use installed and optimized for your machine. be it PyTorch, be it TensorFlow, be it MXNet. I don't know. What do you guys use? Do you use anything else? Okay. It has NumPy, it has Matplotlib, it has everything. It even comes with, I think nowadays it comes with Rapids, which is like a NumPy by NVIDIA using GPU. So if you have used NumPy and you want it to work faster, use Rapids. So the cool thing is that these containers will run on your card. These containers will run on an NVIDIA server, or they will run on the cloud. And that's very comfortable, because every new container is released per month basis. So every month you will have a new container that you can just pull, and it's ready to use. You just need to use your editor, and just off you go. Wait, did I forget anything? Yeah, so I said, yeah. Containers are optimized for performance. You can access them from anywhere. They are free for everyone at no cost. You just sign up to NVIDIA Google Cloud, NVIDIA GPU Cloud, fine, download it, cool. And you know, as I said, you know, these containers have optimized versions of the most popular frameworks. Oh, and they come with examples of the latest architecture. So for example, the model that won Bratz, if you wait a bit, you will also have it as part of the examples. You have, for example, ResNet 50, which did very well on ImageNet. You have it there. So if you want to write your models, you want source of inspiration, you have it there. You have classification, segmentation, reinforcement learning, you have everything. So yeah, the way it works, as I said, on the bottom you have NVIDIA GPUs, then you have the driver, and that's all that you need to install. Then you have Docker, and then you mount container after container, it doesn't matter. That's it. They are platform independent. You like Ubuntu, you like Windows, you like Mac, use whatever you want, download an image, it doesn't matter. It used to be before that in Ubuntu you could use any version of CUDA or whatever, or latest TensorFlow was only compiled for Ubuntu. Nowadays you can use any operating system, it doesn't matter. We take care of it for you. If you want to know more, guess what? It's open source, just get in. Pull requests are welcome if you find any bug, so good. And the second thing that I say we provide is NVIDIA hardware. In the heart, NVIDIA is a hardware company, so we take pride in the quality of the hardware we provide. Our hardware paired with the containers is just better than anything else. The new version of our GPUs is equipped with Tensor cores. Does anyone know what is a Tensor core? Okay, so a tensor, you know that machine learning is basically matrix multiplication. So you have an input, which is a matrix, like an image, where each position is a pixel. You have some weights, which is also a matrix. And then you have your biases that you use to add. So it's a multiplication and addition. So the cool thing about tensor cores is that you can do this in one step. So before it used to be like this, and now it's like this. Just much faster. 12x speed boost, which is not bad at all. We talked before about different numerical representations. So, you know, on the left we have Pascal architecture, which is the old architecture. And on the right, on the three on the right, we have Turing, which is a new one with different floating point versions. We have here FP16, so 16-bit, then int 8, and then int 4. So int with 4 bits, we can still do it. So this is how it looks like. Look at Pascal. That's a disaster. I get old, my hair gets whiter while I wait. You want to use tensor cores. Time is gold. Don't waste it looking at your loss function going down. That's sad. Okay, so I will be closing a little bit. NVIDIA Healthcare, yeah. We are growing. We have some people in Warsaw. I lead the group in Warsaw. We have people in Munich. We have people in Tel Aviv. We have people in Santa Clara. So, well, we interact with people from around the globe for one reason or another, but this is our core work. We are a distributed team. Some people work remotely, some people work at night, some people work during the day. What matters to us is that the stuff gets done and that the quality is NVIDIA caliber. Does this sound interesting to you? Maybe yes, maybe no. But we support research in healthcare across Poland. Do you want to get started in machine learning? Please check our containers. They come with optimized versions, they come with examples. That's the best place to learn. We have all Python, all documented, with benchmarks, with tests, with data sets. Please check it out. Are you a researcher? I understand that here majority would be students, but maybe there is a researcher who is doing something in machine learning or would like to do some stuff or is doing something cool. We like to do cool stuff with machine learning. We sponsor research institutions that do exciting work. Do you require a Tensor Core Boost? We can give it to you. Is your model doing slower than what you would like? We can help you, we know how. We know all the tricks, we have the code, so you don't. We have a close collaboration with institutions. One of them, for example, is the University of Warsaw. We have granted them 35 Volta GPUs for their research in machine learning. Students from Politechnika Warszawska also have access to one of our clusters, DGX1, which has 16 GPUs put together into a big, hairy GPU. They run some projects there, so that's also cool. And last but not least, do you want to be part of our mission? If so, if you are interested in machine learning, in healthcare, if you are good with math, if you know Python, you know TensorFlow, this sounds exciting to you, you want to have a summer internship, want to go to Warsaw, want to go to Santa Clara for the summer, which is pretty cool, let me know, write me an email, send me your CV, look for me on LinkedIn, whatever. Doors are open. We are looking for people. Thank you very much. Okay, so I will be taking some questions. Does anyone have any question?
1 second. I think the person first.
Hello.
Hello.
I have a more technical question for you. Okay.
Don't hit it so strong.
1, 2, 3, 1, 2, oh.
Just shout, I will repeat your question.
Okay. So, which architecture do you think is more suitable for medical image recognition? A 3D convolutional network or a combination of convolution and recurrent network?
Okay, that's a good question. What type of images are you going to?
DICOM.
Okay, these DICOM are part of a study. Is a 3D volume that you want to segment, or? I mean, there are some DICOMs that are single slice, so you cannot use 3D.
Multi-slice.
Okay. So, I mean, the question that I have to do, the answer that I can give you is that according to my benchmarks, 3D convolutions are better.
Thank you.
Okay. If you want me to extend, okay, I don't discard that you can get better by using other things. But if you want to classify a pixel based on the neighboring pixels, it's better that you do it through a 3D convolution.
Okay, thank you.
Okay. Yes?
Is using cluster of your GPUs more efficient than, for example, using Google TPUs?
Okay, so the question is if using a cluster of NVIDIA GPUs is more efficient than if using a cluster of Google TPUs. I guess, but by efficiency you mean like price per hour, or?
Yeah, the price, the speed, and the price.
Okay. So that's a complicated question because these both systems aim at two different things. If you check at price per hour, TPU might be better in price, but NVIDIA is faster. So, you know, if you have to train a model in 1 hour, in Google TPU you will pay this amount of money. In NVIDIA you will pay less because it will take you 45 minutes.
Okay, thank you.
Yes?
Is there any cost of tutorials, for example, for the really beginners in this field of science? For example, provided by NVIDIA to these containers related to?
Okay, so the question is if there are some tutorials for beginners in these containers. It depends what you are aiming for. If you want to deploy an optimized version of ResNet 50, we assume that you know what is ResNet 50 and why it's optimized. But there are materials, I mean, everything that we do is extensively documented. So even the most complicated models are explained step by step. So I would say I would not, I don't know, I'm really not sure. I haven't digged through everything, but we have materials for beginners for everything. Maybe you can complement it from other sources, but you know, it should not be a problem.
And at which place can we find it?
Okay, in which place can we find it? That's a difficult question because I don't know exactly. I don't know, I would advise you to go to nvidia.com. There is a part for developers. So there is a part that you can sign up as an NVIDIA developer, and this connects you to a whole wealth of documentation on everything. You want to know about the driver, you have documentation there. You want to know about deep learning, you have documentation there. So probably, I mean, the best answer that I can give you is to sign up as an NVIDIA developer program. It only requires your email. And there you have access to just a lot of documentation. I'm 100% sure you will find something for beginners there. I mean, if I recall correctly, there are even Jupyter notebooks for beginners. So, you know, that should be, yes.
You were showing that your software helping doctors to classify persons which are ill or healthy. What is the accuracy of your software? How many times your software fails and saying that an ill person is, healthy?
I mean, what our software does is to identify lesions. Now, the accuracy with which it does, it can only be measured against the ground truth that has been provided by doctors. We have different ways to measure this accuracy, mainly, for example, by comparing the overlap. And, you know, the scale goes from 0 to 1. For example, the software that won Bratz is around 0.85. And you might say, well, that's not very cool, because if I have a tumor in the brain, I want it to be 100% accurate. Well, indeed, it's not cool. But you would be surprised that this accuracy is the same that another doctor would get if it would try to segment the same ground truth data. Why? Because a tumor is very hard to segment. You don't know where a tumor begins and where a tumor ends. So even two doctors can give you different opinions. The most important thing for us are two metrics. It's called specificity and sensitivity. Specificity is about making sure that we segment it as true as possible. And sensitivity is about making sure that whenever there is a lesion, we don't say that there is not a lesion. That is very bad. We don't want this to happen. So we try to get as high as possible in those metrics. But yeah, we are not perfect. We are not perfect. That's why we don't aim to diagnose people. We want to be a support tool for physicians. We don't want the physician going through 100 images. We want him to go through the 5 or 6 that we think are the most critical ones. We want to save his time. So that's where we are. Maybe in 10 years, we will be doing better than them, or maybe we do already, but it's hard to say.
In the case of the Alzheimer's study, let's presume that we have trained a model that is able to predict that in 10 years our patient will develop a disease. And is it possible to decode which features of his medical state really cause that prediction?
Okay, so interpretability of what the model is learning is a challenge. There are ways to do that. You can do it. Networks are trained using backpropagation, so it means that we use the gradient, we backpropagate the gradient in order to learn, to approach the optimum. If we do the opposite, with the network is trained, we can highlight those features that have the maximum weight. Based on that, we can look at that and we can say, well, this looks like, might be indicating to something. So there is certain interpretability. What is surprising is that us as computer scientists, we are very limited by that. But for example, when a doctor sees this thing, he can make sense of this because it suggests some patterns that he is familiar with. But yeah, this is a big challenge of deep learning, the interpretability of the features that you are learning, indeed.
Thank you.
So I have a quick question. I understand that the more and more models will be trained in healthcare. The bottleneck is the cost of full scan of my body. So the magnetic resonance or X-ray or any other type of scans are between, 600 zloty to probably a few thousand zloty. And I cannot just jump in and scan myself every month or so. So do you think there are some way have like easier detection of some features, like just measuring my blood, or just taking a selfie or whatever, and from there see if I'm healthy or not? Maybe that's too much, but probably get my point.
Yeah, I do. Okay, so first of all, I don't advise you to take X-ray every month. Yeah, so you will end up in the database of Bratz 2019. That's not where you want to be. So two things on this. First thing is that using deep learning, you say that it has a cost, okay? You take an X-ray, you pay 600 zlotys, but there is someone in a hospital, in some guy president of the hospital has to go and say, okay, I want to buy this machine, yeah? And the same as when you buy a printer. You buy a printer, it has some ink, and you know that it's going to last for like 100 prints, yeah? So you make this decision. You buy a scanner and you say, well, after I have scanned 1,000 people, so this scanner I will just have to buy another one. So if you use deep learning, for example, you are not bounded by the human eye. You have a machine that can work, for example, in less intensity. So it means that 2,000 scans can be, 1,000 scans can become 2,000 scans because you can use the machine at less power. So there you save money. So that is also something that is cool about deep learning. Second thing is that not only imaging. As humans, when we imagine deep learning, we imagine this evil Terminator, or we imagine this, robot, like a human, basically, because we think about it in the terms of a man. So what we try to do first is to try to be better at what humans do. But the thing is that deep learning enables us to do 1 million different things. As you said, can I detect cancer from a selfie? That's very hardcore, but you would be surprised. There is an app, for example, that can tell you if you have skin cancer or not by taking photos of your skin. And this, you have it in a telephone. This exists. You can download it from the Google store. And that is just great. That is great. You can, this doesn't substitute a radiologist. If you have this big mole the size of a tennis ball, just make sure, go to the doctor, yeah? But, but the fact that you can just download something that can give you some input on your health, that is just mind-blowing. And you know, this is definitely possible. The fact that deep learning can put together pieces of information that for us humans are unrelated and produce a result that can be surprisingly accurate means that, for example, if you can only diagnose a condition based on whatever, maybe we can do it with the blood. Maybe it doesn't require you to, I don't know, be opened by a surgeon in order to check inside if something is happening, you know, and then they forget like a scissors inside, and it's like this big deal, yeah? So maybe these kind of systems can learn from your brain, from your blood, for example, and they don't need to cut you open. So yeah, this is something that can happen, you know, we are working actively on these kind of things.
Cool. Anyone?
How much Python, native Python knowledge is required for machine learning? Because we have another modules like TensorFlow, Keras, and other that you need to learn these modules, and is, I don't know, regular Python and object-oriented programming required?
Okay, so is it more like Python, or is it more like TensorFlow, or is it more like general programming? Okay, so, you know, we tend, look, this is a university, I give classes in this university on programming, and I always try to teach students one thing. When we start programming, we think that we write code for the machine, because at the end the machine is going to translate it, it's going to run it, it's going to run it super fast, we want it to be super optimized, we want to cut every possible millisecond. But that's wrong. Why? Because when you work in a place like NVIDIA, with people in Munich, with people in Santa Clara who now are waking up, with people in Tel Aviv who have, for example, we have Saturday and Sunday holiday, but they have Friday, Saturday work on Sundays, yeah? So you cannot write code for the machine. You need to write code for people, because your colleague needs to be able to take this code and needs to be able to do something good with it. So answering your question, it requires you to know TensorFlow, because this is the work that you need to be doing. But it also requires you to know Python or C++. Because this code, you are collaborating with people, and you need to be able to cooperate and to build something bigger with each other. And these people are sleeping when you are awake. These people are working when you are on holiday, and they need to be able to work. That's the power of NVIDIA. It's a very flat company. Everyone cooperates. It's one team. So yeah, object-oriented programming is very important. TensorFlow is very important. PyTorch is very important. And the quality of the work overall is very important.
Okay, a chance for the last question before the pizza. Okay.
So if no other asks, could you briefly compare, because in the image processing we are mostly using convolutional neural networks, and could you briefly say the gains of using recurrent from the convolutional networks?
Okay. So, in short, recurrent neural networks are very useful when you have a time series. Okay? When something is related to what happened before. Okay? When it doesn't make sense to read something in isolation. This is good, for example, if you think about it for translation. You can translate a word in different way if you know what was said before, because there are words that have different meanings, okay? So when you try to classify an image, what you want to do is to classify a pixel based on the neighborhood. These are more related to locality, not time, okay? You don't see, we humans don't see these images pixel by pixel. Yeah, we see the image as a whole. We can focus in some areas, but you see neighborhoods. So this is the way it works. You can learn from the neighborhood, you can pick larger or smaller neighborhoods by the size of the convolution. But what came before, the pixel from up, the pixel from down. This is a very hard question to answer. This is complicated. When you are segmenting 3D data, for example, it might be useful to think about segmenting one image, thinking about the slice that came before. Because the way that the scan is taken is by slices. They slice your body. You have images like stacked on top to each other. So in this case, it might be useful to know what came before. But if you are talking about 2D images, I wouldn't advise you to use RNN. You might get far with it, but you know the top models don't use RNN for that.
Okay, so more questions will be in couloirs. So once again, give a warm hand to our speaker. Thank you.